Hello, I'm Derek McGowan. I'm a maintainer on the Containerd project. I'm joined today by Phil Estes from IBM, who is also a maintainer of Containerd. We are going to give you an introduction to Containerd today. Most of you have already heard of Containerd, but today we will focus on the decisions that you might make as a Containerd user or a potential contributor. Firstly, Phil will go through what Containerd is, where it came from, and what problems it is solving. Then he will go into why you might be using Containerd today or want to use it in the future. After that, I will discuss how to contribute to Containerd. We will go through the high-level architecture of Containerd and discuss the different parts which you may want to contribute to. Lastly, we'll discuss what's coming up in Containerd. All right, let me hand it over to Phil.
Thanks for that intro, Derek. And hi, everyone. It's obviously it'd be a lot more fun to be together at KubeCon like we have for the past few years. Like many of you, it's one of my favorite conferences where I see tons of friends and colleagues across the container world. But we're going to do the best we can and hopefully give you some details on Containerd that are valuable to you in your current role. And hopefully in the future we'll see you again at a conference in the future. But let me try and get us all on the same page and answer this question. What is Containerd? And sure, the default easy response is, well, it's a container runtime. But we all know that term is fairly overloaded, and so maybe it's easiest to see Containerd as being below certain things, and we maybe call those platforms like Docker or Kubernetes, but above a lower layer of what might be the actual container runtimes you think of, like runc, or even some of the other isolators you may have heard about, like Kata containers or Firecracker or gvisor. And so Containerd really fits in this middle spot below these more feature-rich platforms, but above the lower layer runtimes, which actually do the work of executing your container in some environment, whether Linux kernel features or QEMU, KVM. So obviously, if we sit in that space, you could also think of us as a resource manager. So again, we're doing the work on behalf of a platform, and there's another process below us managing the discrete processes itself. We sit in that middle space and become this resource manager for those processes, for their life cycle, handling, start, stop, pause, etc. And again, we deal with the artifacts you're going to need to even start a container. So talking to a registry, pulling the manifest, getting the config and the layers, unpacking that into file system snapshots. So Containerd supports several file systems, Btrfs, overlay, mapper. And so Containerd is that resource manager of you've pulled an image and now you need to turn it into a file system snapshot that can be used by the driver you're using. All these resources have some metadata, they've got dependencies, they have namespaces and other ways to administratively separate them. And so Containerd again handles these for you. And when Derek comes back, you'll see this in an architectural diagram that hopefully helps you see how it all fits together. The other aspect that's important to know about Containerd is that we're a tightly scoped runtime. It takes 100% maintainer approval to increase our scope. So far, the only major change we've made, and it's been several years now, is to bring in the CRI implementation. So Kubernetes has this container runtime interface. There was an implementation started separately that used Containerd. We've brought that within the project, and it's been that way for several years. A couple quick highlights. You may have heard about them already at past conferences, but we're the 5th project to graduate within the CNCF. There are others who've graduated more recently. It's been over a year now since we graduated. In the past year, we've grown in contributors and more companies, and so we now have over 250 unique contributors to the project. We support Linux and Windows. Our Windows support has grown, and we also support multiple architectures. And we've added more recently governed sub-projects like a Rust Lang implementation of the TTRPC protocol, container encryption, lazy image pull support as an external snapshotter. And so again, a lot of things have happened in the last year or two with Containerd. So if you aren't up to speed, there's also a great project journey report that was put out early this year. You can find that on the CNCF website or just by searching for Containerd project journey. So hopefully that gives us kind of a level set of what is Containerd, what are kind of the main components of it, and what's been happening in the last year. So let's move on from there. We talked about what Containerd is. Now let's talk a little bit about where Containerd came from. It was originally built up alongside Docker. It wasn't forked or inherited from the Docker codebase. It was a new project developed around the same time that the OCI was formed and runc was created. And so it was initially that process supervisor that sat between the full Docker runtime and runc. Over the years, it's grown in scope from that initial just process supervisor to a full runtime. Along the way, again, even though some of those capabilities in Containerd overlap with the Docker codebase, the decision was to create new interfaces to take what we learned from those initial years of building the Docker engine and come up with a cleaner API and better separation for the management of containers and images. I mentioned this already, but the CRI was originally this out-of-process plugin, and so that was kind of the last piece that came into Containerd. So again, this growth over years from the supervisor to this full runtime, and then adding in the CRI to be a runtime for Kubernetes. That happened over a number of years. Within that time frame, it was donated to the CNCF. A lot of times there's a desire to compare Containerd with Creo. Creo actually uses parts of the Docker codebase, unlike what I just said about Containerd, and forked, for example, the graph drivers, all the overlay and device mapper and other drivers, and used that as the starting point for Creo, whereas Containerd started with learnings from that initial Docker codebase, but initially and continued to create completely new interfaces. So that gives you a bit of the history of where we came from, how the project started, and where we are today with the full CRI added to that full runtime with registry interaction with container lifecycle management. So, of course, the million-dollar question is, great, should I use Containerd? Of course, you're asking the maintainers of the project who have spent the last 4 years building it, and of course the answer is yes. But you're probably looking for a more nuanced answer of, well, why would I use Containerd? So here's a few aspects before we dig even further, coming at it from different perspectives. For example, are you using Kubernetes? Containerd is a stable, well-supported, very mature runtime for Kubernetes. And as you'll see in a few minutes, most major cloud providers have a Kubernetes offering that uses Containerd today. What about for development? Both Docker and BuildKit, that would be our recommended tools for a developer-facing workflow, but those are using Containerd already today. So maybe you're using Docker or BuildKit, and therefore you're already using Containerd today. You're interested in Edge. Containerd is the most memory efficient and stable runtime. Look at Rancher's K3S, and they chose Containerd again for that reason, for this minimized Kubernetes. Functions as a service, if that's an area you're interested in. Again, Containerd's performance and efficiency have caused it to be selected by OpenFAS for the FASD project. IBM Cloud Functions uses Containerd as the runtime under the covers as well. So these are aspects, maybe you're using Containerd already because you're using a popular cloud provider's Kubernetes offering. But these are all the kind of aspects that we see where people are using Containerd. And it's important to think about this in terms of stability. We initially in 2016 and 2017 talked about Containerd being this core stable runtime. But stability means different things to different people. There's process stability. So again, if you're running a daemon like Kubernetes or Docker or some other daemon, you want process stability in that daemon process doesn't crash on you, corrupt your data, you don't lose containers. That's one aspect of stability we focused on in Containerd. Stability around resource use. You don't want a runaway process or runaway daemon that uses all your memory or eats up your CPU. And so we focused and have done a lot of testing around memory usage, around CPU usage, making sure we don't have spiky resource use, and having the smallest possible overhead for each container about how much extra memory and CPU is required for the lifecycle management around containers. And so the TTRPC protocol was one way to notice that memory usage could be quite large for that management supervisory process. And so we created an additional sub-project that solved that problem and dropped our memory use per container. Again, file system use. We have garbage collection in Containerd, which handles and accounts for that issue of image artifacts and layers being cleaned up when they're not being used. And so these aspects of stability are things we've focused on in Containerd and made progress on over the years and have caused it to be one reason to be a popular choice in various avenues of use today. So we've talked about our focus on stability and on the use cases that exist for container runtimes. And so naturally, what you'll find is that Containerd, because of this focus, is really widely used in production today. And so there's a handful of logos here. There could be many more. But these are all places where Containerd is used in production today. And of course, you'll see cloud providers, you'll see various Kubernetes use cases, and of course, Docker. And then people have used Containerd to build higher level systems. So containers as a service via Fargate or Google Cloud Run or AWS's Bottle Rocket or Firecracker or Weaveworks, Ignite. All these tools and systems and frameworks have been built on top of Containerd. And each one of these use cases is well supported by the Containerd framework and model of having a clean API, clean separation. People can use various aspects of Containerd without using others. And so we've seen huge growth over the years in both Containerd as a building block, but also leading to a wide use of Containerd in production. And that's led to even a lot of contribution. So the device mapper Snapshotter from the Firecracker team, or other features that have been contributed or developed, or external projects building around Containerd that you can find today. So again, given that, it's natural that you'll see when you look at the CNCF annual survey or Sysdig's annual container report, the use of Containerd, especially in production, has grown year over year every time the surveys have come out. And you'll see that given we know Docker uses Containerd, when you combine Containerd and Docker usage together, it is the lion's share of container runtime use in the industry today. So I talked about this a few minutes ago, but effectively, because of all these use cases, because of all these implementations, if you're running containers, you maybe already are using Containerd in some way. Are you using Docker? Then yes, you're using Containerd. If you're using BuildKit, then you're already using the Containerd API. Are you running containers in a cloud context as a service like Fargate or Google Cloud Run? Then you're already using Containerd. And we've, of course, mentioned the common Kubernetes use case. So all the cloud providers managed service offerings use Containerd. And so you probably may already be using Containerd today. If you have a use case that hasn't been represented here, we'd love to hear from you and hear how you're using Containerd. But at this point, it'd be a great time to transition back to Derek to talk about not just using Containerd, but contributing to it. So pass it back to you, Derek. Thank you.
All right, let's discuss how to get started contributing to Containerd. Most of you are already using Containerd in some form. We're still happy if your only contribution to Containerd is attending this session and learning more about Containerd. We hope you never encounter issues while using Containerd, but we all know that's inevitable with any software. Please contribute by filing those issues on GitHub. We also recently opened up GitHub discussions for Containerd. This operates in place of a developer mailing list and is a good place to ask and answer questions. All maintainers are also available on Slack for guidance. Even if you are just filing issues, it is good to understand the architecture of Containerd. It will not only help you diagnose problems, but also help you understand what components may be affected by your issue. If you want to contribute code, knowing the high-level architecture will help you understand where to contribute. It may also help you align your particular interests with different parts of Containerd. If you are integrating with Kubernetes, the CRI plugin is a good place to contribute. If you like lower-level system development, runtimes are a good place to start. If you'd just like to hack around with container technologies or have a new feature you want to try out, the Containerd client provides good flexibility for that. Usually contributing to the client is the best place to start. That is where you can get started pretty quickly. As a user of Containerd, the client is the first place you will interact with. If you are building a system on top of Containerd, the client is what you will be working with. You can see in the diagram that some core functionality that is often associated with container runtimes is implemented here in the client. An example of this is container management, which handles creation of the OCI specification, preparing the container snapshots, as well as starting individual container tasks. Image pulling is also completely implemented inside the client. Because of this approach, clients are mostly limited to using our Go library. Even though Python, Java, or another language could talk to the Containerd API using gRPC, basic functionality would need to be re-implemented to use the full runtime. The CRI interface is probably much easier to work with if you are not implementing your project in Go. One of the first things you'll come across in the client is the options pattern. We realize not everyone is a fan of this pattern, and we always appreciate feedback and pull requests to make the client better. Any software can get complex really quickly. Sometimes adding simplicity in one part can lead to complexity in another part. With Containerd, we chose to keep the core as simple as possible. By defining clean, simple interfaces inside the core, that meant the client had to have more functionality and configurability. In the Containerd core, there may just be generic variadic options on a core type, but in the client, you will see these with options used on these types to implement a feature. You will commonly see this used, for example, for labeling or filtering on the different types. We were also hoping this would allow clients to include their own opinions rather than be forced to work around opinions in the Containerd daemon. The core of Containerd contains the components we consider most critical in terms of stability. Here we define the main data types and interfaces used by Containerd. If you think Containerd overuses interfaces, this is partially intentional. We want data and operations flowing through the core and everything else wrapping those types or using data that is tracked by the core. The core has the main implementation of these interfaces, and these interfaces are extended and used all the way to the client. The design is such that all data flows through the core, so that plugins and other components don't need to store data. This is important because we have implemented garbage collection inside the core metadata store. So if data is being used somewhere else, it is really hard to track that data and make sure that it is removed when it is no longer needed. This makes Containerd stable by keeping storage and memory usage stable. It also helps avoid data inconsistency and random crashes. We don't expect as many changes in the core relative to other parts of Containerd. Features generally aren't implemented inside the core. However, some features may require some core changes. If you have a high-level feature which requires a bunch of changes to the core to implement it, that is usually not the right design. However, some features require small changes inside the core. So, for example, we recently added a feature to support remote snapshotters. The high-level feature of remote snapshotters is not something that the core knows anything about. But one functionality we did add to the core was the ability for the snapshotters themselves to report that they already know about a snapshot as it is flowing through the core. So when you go to create a new snapshot, you can pass information that says, this is the target snapshot that I'm trying to create, and it will pass that to the backend. The backend now can actually communicate back up to the core to let it know that it already has that snapshot. That allows the client to know the snapshot is already available as a remote snapshot when it sees the core report the snapshot as already existing. Meanwhile, the core has no knowledge of what a remote snapshot is. It is really important for us to keep the core of Containerd unopinionated to make sure we don't get feature creep showing up in the Containerd daemon. We also don't want opinions to show up in the daemon so that later on, new features or requirements are limited by previous opinions added to the core. For the underlying runtime, there is a component in the Containerd daemon and an external shim for managing container processes. The runtime in the daemon is responsible for starting up new runtime shims. It will pass through the OCI specification and all the commands to the shim. The runtime shims are the boxes on the right side. These shims are what actually own the container processes. The containers are parented directly to the shim. The containerd daemon will talk to the shims using a lightweight gRPC protocol called TTRPC. We use this lightweight RPC to reduce the memory footprint of the shim. If containerd gets restarted, it will reconnect to the shims in order to send commands to the container. There are many different runtime shim implementations. The runc implementation is the most common. There is runhcs for running on Windows. There's also a few sandbox shims, such as for Firecracker or Kata containers. Since the shims only implement this RPC interface, anyone can implement their own shim to be used by containerd pretty easily. Containerd just needs to know about the shim binary in order to use it to run containers. Plugins can call into the core of containerd, and the core can call out to different backends. The backends themselves are also pluggable. For example, all Snapshotters are implemented as plugins. Each plugin can define their own configuration, which gets included with containerd's global configuration object. If you have a gRPC service, it can be added as a plugin and call into the core services directly. CRI is shown in the diagram as a plugin. It is just registered as a gRPC service plugin. Even though CRI is very important and big enough to have its own core, we don't include it as part of containerd's core. This is because CRI consumes the core services, but today it is implemented completely outside the core codebase. In containerd 1.5, we are looking into bringing the CRI codebase into the main containerd repository. This will allow us to merge some of the core components of CRI, such as pod sandboxes, with the core components of containerd. This may lead to new types and interfaces inside the core related to sandboxes. In fact, there is already a proposal to add a sandbox API to containerd in 1.5. Including your own Snapshotter plugin is pretty easy. You can compile in the Snapshotter and register it as a plugin, just like every other built-in Snapshotter, or you can implement your Snapshotter as a proxy plugin. A proxy plugin allows the Snapshotter to just implement containerd's Snapshotter gRPC API and configure containerd to talk to your plugin over a Unix socket. The proxy plugin approach is great for experimenting with plugins without having to compile containerd or ship your own binaries to include your plugin. In the client, there are many options for customization. By default, the containerd client will use the proxy services which communicate with the containerd daemon through the gRPC API. However, a client can be instantiated with any custom implementation of a service, even allowing clients to operate completely without a daemon. You can also add your own resolvers. Resolvers are what are used to push and pull images to containerd. The default implementation communicates with a Docker registry using the standard OCI distribution API. However, you can implement your own very easily if you have a different or faster way to distribute images. Okay, going back to the whole containerd diagram, you can see how operations flow from the client on the left all the way to the runtime and backends on the right. The components on the left tend to be more stateless. The components on the right have more state. Even though our garbage collector is in the middle, it tracks resources used by all the backends, but it operates completely invisible to the client. Our end goal is to track any resource which may be used by containerd to guarantee the long-term stability of the runtime. Containerd 1.4 has recently been released, and you can start using it today. It includes support for cgroups v2, improved SE Linux support for remote snapshotters, and support for CRI on Windows. If you want to hear more about remote snapshotters, attend the deep dive session for containerd. The containerd 1.5 roadmap is currently being decided on. As I mentioned before, a large item will be merging the CRI codebase with the main containerd codebase. We also have ongoing work to introduce a new sandbox API and core sandbox interfaces. This will not only allow for better integration with virtual machine sandboxes, but also allow us to clean up the way pods are managed by containerd. There's also work going on to improve the way system resources are managed by the runtime. This relates to improving interactions with resources and tying them into the container lifecycle more cleanly. Feel free to join the discussions today for containerd 1.6. There are discussions about a new node resource interface which operates in the container lifecycle similar to CNI. There's also discussions about the possibility of introducing a new version of the CRI API. So if this is something that interests you, come join the conversation. All right, that's all we have for you today. Thank you for joining. I'd also like to give a shout out to Sue McGowan for helping film and edit this session. Bye-bye now.